a heliophysicist in training, because we really aren't heliophysicists so much. I am a solar physicist with a stellar astrophysics background, and I was asked to talk about the solar spectral irradiance and the solar wind. Now, in order to do that, I really have to take you through everything that causes the solar spectral irradiance and the wind. And in order to do that, I thought I should show you lots of things that are happening on the sun. And showing you things that happen on the sun require movies that are played best out of Keynote, and Nice Meeting doesn't do that. So no, it is not mirroring anywhere. I have exported it as a QuickTime movie that'll be put on the web, so you can look at the movies, and we'll also have the PDF there. Potentially by the end of the day, if Kendra can get it there, but if it takes until Monday, you'll have it. So for now, you'll have to work off of this. Now, let me start first with two questions. How many of you have had classes in stellar structure and evolution? That's pretty good. And how many of you have done radiative transfer? Excellent. Okay, I can go through this in no time. We'll be done sooner than I thought. So what I'm going to do is take you through all of these topics. And I would ask you to just ask a question. If you have a question, just raise your hand. You can't type it in on the Nice Meeting thing. I won't see that. And interrupt me, because I'll be happy to answer the questions. The talk comes in two parts. One that really focuses on the spectral irradiance. That's the first two halves. It's a little longer than midpoint, so it'll take about 50 minutes to get through that. And the second part on the solar wind will be a little shorter, not because it's easier, but because much of the foundation of the wind, of course, has to be discussed already when I start talking about the irradiance. So I'm going to start on this end with the atmospheric structure. What is it that we look at in order to understand what makes the sun's spectrum, the solar spectral irradiance, and the total output of the sun that comes towards the Earth, the total solar irradiance? And then from that point, I'll start building it up into the variations. What's making it change over time, and what are the various contributions that make it change? What do we learn from them, and how do we think about them as we start thinking, going into next week, how all these things impact the planets? So if we started from what Mark Maltman said yesterday, if we took the astrophysicist perspective that I took issue with, and we disregarded the magnetic field and all the dynamics, and we just set all of the variables x to they're not varying. What you'd be looking at is a sun that looks like that, basically a big white disk. Now, one of the things I'll have to ask you about radiative transfer is that disk goes dark towards the edge. I've tried to reproduce the intensity much like you'd see the real solar disk if there were nothing else going on under the sun except radiation coming out of that atmosphere. So why does the light dim as you go toward the edge of the disk?
Due to the limb darkening, the line of sight takes the large paths to the limb side. So due to the lesser temperatures in the photosphere from upper layer, it gives the limb darkening.
Due to the what?
Limb darkening.
Opacity is part of the problem. Yes, light comes from different layers in the atmosphere. And light gets out most easily. If I reference anything, my gravity is going to point straight down, because that's the easiest way to think about it. This is the atmosphere. Light goes out that way most easily, because that's the shortest path out. If you incline it, it doesn't get out as easily. But that's not the reason it goes dark towards the limb. There's one other ingredient in that you have to think about. The temperature gradient. As we look further out towards the limb, you're looking at an ever more inclined light path out. And that means it has a harder time coming out. It comes out from a higher layer, and the higher layer is slightly cooler, and because it's cooler, it's fainter. So that's the basic principle of creating a limb-darkened disk. But on a star like the sun, there's no way you can do this without dynamics. The outermost layers of the solar atmosphere, the outermost layers of the solar interior are too opaque for radiation to come out very efficiently. There's another mechanism that transports energy much more efficiently, and that's the reason of all the irradiance variations we're talking about. It starts convection. And you can hardly see it in a white light image, but there's this slight mottling here on the real sun image. That is the overturning convection that carries thermal energy to near the surface from where the photons can then suddenly escape without further interference into space and come towards Earth and any of the other planets that are in its way. Now, that is also a very noisy process. The velocities involved reach up to very near sonic speeds in some places. In fact, in some places, they shock as the material comes up. Well, some new material below it keeps coming up, so it's being pushed to the side. And as it's moving to the side, it's losing energy, darkening, and at some point it's cooled and begins to fall down, because as it cools, it becomes denser, heavier, it falls down. That overturning motion on the smallest scales that we can see, and probably the smallest scales that really exist, are of the order of the size of Texas, Germany, Nigeria, a good part of India. It's about 1,000 kilometers across. And it takes only 10 minutes for the material to do that. So the velocities really are of the order of a kilometer a second. Near the downflows, they reach several kilometers a second. The sound speed is 7 kilometers a second. So it gets very noisy. That noise generates, that noise is sound waves, and the sound waves propagate up and down, and they do something interesting, even from the perspective of irradiance. Now, this overturning motion can be studied in the computers nowadays very well, because we can simulate hydrodynamics. That's easy in a sense. The hard parts are this is a very, very strongly stratified domain, because the temperature gradient, the temperature drops so rapidly that there's lots of pressure scale heights you have to put in. The most difficult bit of this kind of simulation is to do the radiative transfer right. It's very difficult to get all the photons out in the right way. But it leaves the sun as an undulating surface. It's not flat. It's undulating, but it's incredibly nearly flat, because it's 70 out of 700,000 kilometers that are roughly that up and downward motions. Those motions generate sound. And if you look at a Doppler movie like this, and I'm sorry it's so small because I couldn't find a good one that played fast enough that showed all these things, the whole solar surface is undulating up and down, because all these sound waves set up the sun in a mode of resonance. In fact, of something like 10 million individual modes of resonance. It's like you're hitting a bell. Think about it in a bell in a sandstorm. It'll start to ring at its own frequency. And these motions go up and down with speeds of up to several hundred meters a second. So they're pretty fast motions, but not nearly as fast as the sound speed. It's a gradually undulating process. These P modes, as they're called, the pressure modes, the sound waves that propagate through the interior of the sun, tell us lots of things about the interior, but they in fact even show up in irradiance. So this is, I'm now going to start talking about irradiance, the highest frequency part of the irradiance variations. If you make a diagram of how much power there is as a function of frequency, there's that interesting domain here that the very highest frequencies, the sun doesn't generate all that much, and if it tried, any pressure fluctuation of high frequency that tries to get through the photosphere basically is damped by radiation. You compress it, it loses its energy. It just won't oscillate. It has to oscillate slowly enough that it can start doing this kind of resonance. Around 5 minutes, you see that forest. I'll show you the forest in just a minute. And as you go towards longer time scales, there's still a lot of power in the irradiance. You can actually see in a star like the sun that you can't resolve the noise generated by the granular motions, even if there's no way you can ever resolve the granules in a telescope. And as you go towards longer and longer periods, that spectrum continues to go up. And I think, I'm going to just zoom into this. There's all these individual P modes that I won't talk about. You can read about those somewhere else. They tell us everything about the internal structure and a lot about the internal dynamics of the sun as a star. They are visible in the irradiance. On longer time scales, it's remarkably hard to find spectra that do this for anything longer than sort of the 10 days that I can get to here. Not because the sun isn't variable at those periods, but because then you start having to worry about the stability of your platform that you're measuring it with. So not too many people actually publish it, although we know the sun keeps going towards higher frequencies up to rotation periods, its own rotation period of a month, a few months for spot and active region development, and then the entire solar cycle that sits up on it by the time you've reached this point on the diagram here. If you wanted to compute the spectral irradiance from the sun ab initio, you'd have a really tough time. First of all, you'd have to say, I want to be able to measure it Well, we live in a wonderful atmosphere, beautifully suited for us. It's a terrible thing for an astrophysicist because it absorbs things that sit between what we want to study and our telescopes. So the easiest thing to do is go to space and measure something like this, the solar spectrum. And even in that spectrum, it's just incredibly full of spectral lines. There's lots and lots of ions around there that take light out. So doing a computation of this is really difficult. What most people do is say, we give up on this, we'll just measure it, and then do the comparisons, and then start studying the variability of that. Now, here's a movie of a simulation of those convective motions. So each of those cells is of the order of 700 kilometers across. Every time you see a new cell generated in this pattern, the equivalent of 10 to 15 minutes has passed. And then there's the right-hand diagram. And this is what Sabine's talk was about this morning. If you stir a electrically conducting fluid vigorously enough, you generate magnetic fields. So even in these dynamo simulations nowadays, we are generating magnetic fields, sort of pepper and salt magnetic fields that show up all over the place as we observe on the sun. I'll show you the real sun in just a moment. But from this point on, it's the larger scale motions that become the dynamo that form the larger scale patterns that are most prominent in anything that has to do with the irradiance. But you have to remember that field is everywhere. It threads everything. And on a scale of the granular overturning, it's a mess. When someone uses the term quiet sun in conjunction with the word easy, they haven't thought about this. It's the active sun that's easy. Separated scales, it is easily visible, big dipoles. This stuff is the hard stuff. We just pretend it's easy because it doesn't do terribly much, we think. It does couple into the larger scales. There are all sorts of induced currents that probably run around. But that smallest scale field doesn't do terribly much. But it is the seed field out of which you build the larger and larger and larger scale. So at some point this transitions into what we call, as a solar and astrophysicist, the dynamo, the one that does the global dipole field. There's a lot of processes that go on. And I could talk to you for a whole school and then some about all of the details. And sometimes you see diagrams like this that essentially make these summaries. Well, we've got these small convective motions. There's a hierarchy. There's the larger convective motions, what we call the supergranules, that are sort of 20,000 kilometers across. They take a day to overturn, and scales in between. They all generate waves, sound waves that travel in and out. So, what happens to these sound waves? If you send out a sound wave that has a long period, you're basically lifting the atmosphere, and it'll fall down, and you're lifting the atmosphere, but you're not compressing the atmosphere. So basically, that whatever you're trying to compress is running ahead of you fast enough that you're not compressing it. If you don't compress, you don't generate a force, a back reaction force. So you don't have a propagating wave. What you have is an evanescent wave that essentially lifts the atmosphere and it goes back. It goes down, and that's where it forms these trapped waves. The shorter period waves, the ones that actually are oscillating and compressing as they go up, they do run up. And as they run up, they see this tremendous density gradient. I'll show you the numbers in just a moment. And tremendous in the form that this is what most people show you. I have to show you what it really looks like. If you do the aspect ratio right, it should look like that. Okay? Sorry, one step at a time. It should look like that. It's really very, very stratified, very, very flat. But these waves can't get through there. They shock, they form shock waves that dissipate, that form part of the heating that creates the atmosphere. But the bulk of the outer atmosphere of the sun, when we talk about the bulk of the chromosphere and all of the corona and all of the wind, is something that has to do with the magnetic fields there. And I'll show you the structure of that in just a moment. So, I already answered my own question. I was ahead of schedule. Now, here are the numbers. I'm using terms that have different definitions to different people. So you should be aware of the fact that sometimes people mean something else when they use one of these words. Formally, the photosphere is the surface of the sun, which is the layer from which light can suddenly begin to propagate towards interstellar space without further interference of the matter that sits up there. Now, that's not entirely true, but the bulk of the light goes out and just flies away. That's a very well-defined layer. It has a thickness of about 70 kilometers, as I said, out of the 700,000. That isn't even close to the skin of an apple compared to the apple. It's very, very thin. So it really looks like a surface. Above that sits something we call the chromosphere. The chromosphere can mean either, to some people, a temperature domain. It's 10,000 to 20,000 Kelvin. To others, it means what I've been trained in. It's a definition in radiative transfer. It's transparent at almost all wavelengths, except in some of the strongest spectral lines of ions. And that's why when we look at the chromosphere, we pick the lines of the abundant elements of fairly low ionization stages. We look at them in H alpha, a neutral hydrogen, but a high energy excitation line, or we pick singly ionized calcium, or there's lots of singly ionized iron lines that you can look at. For the rest, it's transparent. And then there's the corona. The corona is the part that is essentially transparent to any light, except if you're a radio aficionado and go to really long wavelengths, but it's basically transparent in all light. And the density contrast is astonishing. We go from 10 to the 23rd particles per cubic meter in the photosphere to something like 10 to the 14. So you get down by 9 orders of magnitude. That's more than the difference between the atmospheric thickness that you breathe and water. It's a pretty abrupt change from a dense photosphere into almost vacuum, but not quite. The corona, by the way, is a vacuum that's a higher vacuum than what we call outer space when we think of the orbit of the International Space Station, for example. There's hardly anything there. The only reason I can show you pictures of it is there's a lot of it in terms of volume. Density is very low, volume is very large, so the little bit that radiates is still visible. Temperatures, that's another interesting one, of course. As you probably know, the temperature goes up by almost a factor of 1,000 as you go from the photosphere into the corona. That's part of the problem we're trying to understand. And now let me take you through the pieces. If you look at a still magnetogram like this one, we have these wonderful terms that we use all over the place to describe these structures. And the green ones in any one of these images I'm going to show you are the ones you can actually see in the image. But there are other structures that are there. There's a coronal hole there. There's a filament there. Like, what are you talking about? There's nothing there. Well, that means because not all wavelengths show all structures. You have to tune your instrument to the right wavelength to see the structures that you're interested in. That doesn't mean they're not there. You're just not seeing them. How do we measure this magnetic field? With a magnetograph, but what does a magnetograph do? What does it measure in order to quantify the magnetic field? Yeah, same amount effect. And polarization, and that's the key part. Mark yesterday mentioned that if you pass light through a magnetic field, a plasma threaded by a magnetic field, you'll see that the lines are split. But on the star like the sun, the splitting that occurs is actually, except if you go way into the infrared, in the visible, that splitting is much less than the thermal line width of the ions moving around. So that signal's just washed out. However, it also polarizes the light, and that signature remains. So if we use polarization filters in sets of combinations of circular and linear polarizations, we can, from that, infer what the magnetic field is. So it's in a sense, it's the Zeeman effect, but not just the line splitting. It's the polarization that goes with the line splitting. Now, that magnetic field is, in fact, incredibly dynamic. And if you look at any process at its own scale, it always becomes very interesting, except that the sun has the annoying habit of rotating. It rotates at about the same rate as an active region takes to evolve. So you can see the beginning of it, but not the end. Or you can see the end of it, but you didn't see the beginning. And we still don't have, although the stereo spacecraft look at the sun now with the Solar Dynamics Observatory from all sides, we can see the full sphere. We don't have magnetographs that cover the full sphere. So what we do is put that into a model, and if you unwrap it into a complete longitude versus, in this case, sine latitude, it's basically unwrapping whatever that sphere is doing that way. You can see the front of the sun drift by in that oval, And we have a model that takes over whenever the front of the sun isn't visible and moves these charges, these magnetic concentrations, the flux tubes, into which the field is patterned around. And you can see that things evolve drastically. Look at that region here. It'll spin back in just a moment. Yeah. Okay. Here, you suddenly see it appear. Fields, of course, emerge on the backside of the sun that we can't see. So in a model like this, they suddenly spring to life. But there's a little more. There's one other thing that I'd like you to see here. If you look at the magnetic field concentrations, just pick any one of them. They just wander around and disperse. Why does the field disperse? Neural flows sweep. Right? The largest scale fields sweeps. It should pick up all of the polarities and just sweep them into whatever the direction of the large scale flows are. But they just disperse. There's a term that showed up in Sabine's equation this morning. There's a diffusive term. That's not what's happening. But you have to realize this. The diffusion, the conductivity of the solar photosphere is fairly good. It's not astonishingly good. It's like copper, I think, at room temperature, if I have the number right. The reason why diffusion, the formal diffusion, doesn't work on the sun is that the scale is large. It would take forever for the field to disperse over any noticeable distance if you relied on the real resistivity of the medium. What happens is the medium is bubbling. It's got all these convective motions, and all these flux tubes are caught and moving with these convective motions. And if you randomly walk anything, random walk becomes diffusion. So on the largest scales, the field diffuses because of the driving by the convective motions. It's basic. Okay, I can describe it to you in more detail. What we do is we take a magnetogram, we parse it into bits and pieces and put every one of these pieces as an atom walking around in our model, and they can do whatever they like, bump into each other, opposite polarities cancel, random walk disperses, until the new front of the sun comes by, and then we just replace it. And we've run this thing for the last over 16 years of data, so you can look at a 16-year-long movie of this. I'm only showing you, I think, a month and a half of that. Okay, back to the magnetic field. Above, that magnetic field threads the surface of the sun, into which, again, all these structures are there. And now I'm like, you're only seeing one. How come I am only seeing one structure? I'm only seeing the sunspots. I'll give you a little bit of a lead. It's because my instrument wasn't sensitive enough. I could see more if I did look at it really carefully. I could see the little bits of magnetic flux tubes, and I'll show you that in just a moment, out here. But there's lots of things we don't see. The reason is the magnetic field does not noticeably change the intensity of the light unless the magnetic field can change the atmosphere from which that light comes. And it can do that only if the field is strong enough and if the patch is large enough. So how does that work? Okay, this works like this, and this is part of what you need to understand in order to understand the irradiance variation that has to do with faculae and sunspots. The sunspots are the largest concentrations of magnetic field. What we call the faculae, these little bright areas around here, are the signature of the surrounding magnetic field that's smaller in concentration. All of it, by the way, is about the same strength. It's all about 1 to 3 kilogauss. It's not like weak field and strong field. The weak field wouldn't show up in this at all. So you've changed the appearance, and you've changed you've got a fixed field strength, and the field strength somehow changes the appearance in these images. How does it do that? Well, it does that this way. Imagine a tube that is a flux tube. Magnetic field sits here. No field outside, field in here. Why do I do this? I do this because of the drop in density. The field expands as it adjusts to the surrounding density. Somehow, at this level of the surface of the sun, radiation goes out. Energy is lost. In order to maintain the brightness, I have to replenish that energy. I have to bring new material up that's still hot from inside and keep overturning that. If the field becomes strong enough to impede that motion, I can't maintain the temperature. So the temperature begins to drop. As the temperature drops, what happens? Two things happen. Pick one. Something that's cooler is darker. So it begins to darken. But it also can't maintain itself against gravity because a lower temperature means it's going to just slump down under its gravitational stratification. So it goes dark and it goes down. And that's what causes a sunspot. That what we call the surface of the sun, from where the light escapes, is the bright surface here. But in a magnetic field, in a strong magnetic field, the photosphere is actually lower and cooler. Okay, so that creates a dark structure. In fact, that creates, I thought that was a really neat way of looking at what's called the Wilson depression. If you look at a sunspot from the side, rotates to disk center, goes back to the side, it looks like a little dish. And you can actually see the distortion, and you can see that that central layer is lower than the surroundings. It's a neat experiment. No, there's not that much that motion because the field is so strong, hardly anything really happens. Well, that's not true. If you had a really good instrument, there's lots of dynamics going on. But the regular overturning convection is stopped. That field just sits there. The only way that it can do this, that's a completely different story, is if it ran a current through it and the current changed, and then you would be changing the structure. But that's not a vortex in that sense. So, is there a question? I do not wish to get into the penumbra. Save that one for right after the break, because I'll be happy to come back to that. But that's not a story for the irradiance. That's a story for magnetic fields. Now, this leaves me with the question, these tiny concentrations are bright. Why are the tiny concentrations bright? That's a slightly tougher question. Now, for this spot near disk center, we're looking straight into the dark bit. Now imagine that you're looking at it from that angle. What are you seeing? If it's small compared to its depth, what are you looking at? The wall. You're not looking at the bottom, you're looking at the wall. The wall is a part of what elsewhere would be the interior of the sun, right? Because it's lower, it's actually hotter than the surface. And it radiates out its light. So the walls are bright. So if you make something small and tip it, it becomes bright. And that's the whole story of irradiance. I'll show it to you in just a moment. But first, let me go up a little higher. Above that atmosphere, above that magnetic field, the whole atmosphere is threaded by that magnetic field. And this helps to structure the atmosphere. So if we go up in temperature a little bit, suddenly we see that wherever there's magnetic field, it is always brighter. But it's always brighter because that magnetic field deposits additional energy into those domains that make it radiate. Even though it isn't optically thick, it is brighter because it has additional energy. And it becomes more and more pronounced as you go up higher and higher in temperature. And that's roughly the same as saying higher and higher in atmosphere, in geometric height, but that's not true by the time you get into the corona. The solar atmosphere is very highly structured in any direction. So don't think of height and temperature as equivalent in any sense, not nearly as much as they would be in the Earth's atmosphere. And it's very dynamic. Just in case you forgot about it being dynamic, I'm going to show you a little movie of just that little snippet of the sun there. Not quite that, but something equivalent to it, recorded from a ground-based observatory. And it's a beautiful movie. It shows in H-alpha, hydrogen spectral line, the movements of all these, well, what is it showing? Actually, the magnetic field, because the matter is tied to the magnetic field. The magnetic field is moving around, and you see this entire structure that's swinging and moving. And these are, you could say, on the one hand, sizable structures. I'll give you the size for scale. I'll come back to you in just a moment, Fran. That the Earth is a pretty big object. So the smallest thing we can see on the Earth is something the width of the Rocky Mountains, or the width of the peninsula that I happen to live on, which has San Francisco on it. It's not terribly good. If you thought of it in terms of, well, how good is it if I had to build a telescope? That is a 10-cent piece seen at 10 miles distance. These telescopes are astonishingly good, even looking through the Earth's atmosphere. But they're 1 in a million shots, literally. You can take 1 million hours of recordings before you get something this good, and even then you have to put a lot of computer power into restoring the images before you see it. That's why we all like to go to space. Fran?
So you said that versus you're seeing something else that's changing all the time?
You're mostly 3 slides ahead of me. Can I come back to that? It's a very good question. I was going to ask you the same thing, so very good. Every wavelength we pick, now we're in the extreme ultraviolet, so only light you can see in vacuum, shortward of about 200 angstroms. Moving into ever shorter wavelengths, so equivalent of higher temperatures, and you see more and more of these structures. By the way, notice the solar surface has now gone dark. It doesn't emit at these wavelengths. We only see the highest atmosphere, the corona. And the corona is full of these interesting structures. We can now see all these things that I've labeled, except the sunspot, because that's a deep down structure that we don't see anymore. You can guess it's there because it's got this nice fan around it, but you can't actually see it anymore. But we see all these structures that we call loops, these fine strands that dominate all of the atmosphere from the chromosphere on up. Why do we see loops? It's magnetic field. It's a good clue. Magnetic field is one clue. Second clue, diffusivity. Third clue, energy. You put energy on a magnetic field line with a plasma on it, what does that energy do? It cannot go sideways. It can go along the field, it cannot move sideways. So it's going to spread out. Electrons are really good at conducting energy around. It's going to spread the energy around along the field line. But the material is so short-lived compared to the time it would take for things to diffuse that you've essentially created one-dimensional atmospheres that just outline the magnetic field. So they're one-to-one structures in most cases, except when life gets interesting to Terry and things reconnect, and then material can jump from one field line to another. It's frozen in. So diffusion can be ignored, and that's true for just about anywhere. And that also means, and I'm going to show you this just very briefly, that you can write down equations that the energy transport in the corona, if it's not exploding, if the field is stuck, and you're just looking at how does energy move around, is a pretty straightforward equation that says energy in, heating, is energy out, radiation, and energy redistributed. You can compute this. People have spent 40 years doing this. The difficult bits are we don't know what comes in, because we still don't know really what heats the outer atmosphere of the sun. Yes, we do, but there are lots of pathways by which these magnetic energies can be converted into what eventually is a thermal energy that radiates out. And it's really difficult to write conduction down, because in order to write conduction down, you have to know the cross-section over which you're conducting. So it's not a trivial exercise. And on top of that, of course, there are flows that are often so fast that you can't ignore them anymore. They're near sonic or worse, and you have to include them. Now, one more question before I start assembling the irradiance picture. Yes? I sidestepped one part of the question that Fran asked. Why do we see fibrils? We see fibrils in part because energy is distributed only along the field line, and in part because something puts energy on a particular field line in different ways. And that's getting closer to what you're asking. We don't really know why certain field lines are picked out as opposed to other field lines, so we don't really know that distribution all that well. This is a set of interesting images. Occasionally, Mercury goes in front of the sun, and it won't happen for a while anymore. When is it? 2018, is it? One more. And this is a series of snapshots in different wavelengths, in the visible light coming from the surface of the sun, in the ultraviolet, and in the EUV at 171 angstroms. And I've basically just put a series of pictures next to each other. So there's time difference going from one to the other. Here, Mercury touches the photosphere. Here it doesn't, and then there's something else funny happening. There's a strong brightening there. What's happening in these pictures? Sunlight has to get out. It gets out differentially depending on the opacity of the medium. So the sun has a different size in different wavelengths. Every wavelength has its own size. That's part of the problem of computing this whole irradiance picture. And by the time you get to this wavelength, the light is completely optically thin. So there's no such thing as limb darkening. In fact, there's limb brightening, because now as you look through towards the limb, you're looking through a thicker layer. And there's a jump, because when you reach the real limb, as in that's where the opacity for that wavelength just drops away completely. Suddenly I'm looking not just through the front side of the sun, but I'm seeing what's on the back side. So it doubles in intensity. And here is essentially the chromosphere. So if anybody ever shows you a picture where these limbs align, you can tell them you've made a gross error here. You've basically ignored the fact that there's a layer of about 4,000 to 6,000 kilometers in thickness, depending on where you look and what wavelength you pick. That's the chromosphere. That chromosphere takes light away, if you're talking about EUV light. And it modifies any light that comes to you in any other direction. It's always there. It just was very obvious in this kind of a picture. Okay, so now we have this horrible beast. It's ringing. It's creating all sorts of waves. It's creating all sorts of magnetic fields. And out of that, we're trying to figure out what is the light that's coming out. Well, most of the light coming out, if you measure how much light comes out as a function of the wavelength, I think I'm beginning to lose my pointer, as a function of the wavelength, most of that gray line matches the dashed line. The dashed line is a black body. And a black body only exists if no light escapes. So you already made an error here. You can't have a black body from which light escapes. But if you make the hole small enough, you can get sort of black body. And most of the solar surface radiates as if it were a black body at about 5,770 Kelvin. At the very longest and the very shortest wavelengths, the opacity isn't enough to shine like a black body, so the brightness drops below the curve. And at the very shortest wavelength shown here, there's even less, and yet it becomes brighter. And the reason it becomes brighter on that very short wavelength end is there's hardly anything there, but it's incredibly hot. So it tries to be bright, but it can't quite get to a black body temperature, but nevertheless, it's a lot brighter than the black body of the 5770 Kelvin surfaces. And now I'm going to go into the last bit. Oh, look at that. I gave you the answer. What is the color of sunlight? Everybody says it's a yellow star. Is it a yellow star? It's got lots of colors of light in it.
Space art often shows the end of the Earth with the sun as a red giant star.
Yeah.
In the sky, and it always stop sign get saturated with red. Actually, in fact, quite a lot of light.
But it would be pretty much redder than it is now. Then again, we wouldn't be there to see it. But right this instant, the color of sunlight is, it's white. Why are the clouds white? Scattered sunlight, okay? The sun is a white star. We think of it as yellow because as it gets lower in the sky, and we can actually start to look at it, much of the blue is scattered into what's the nice blue sky. And you could say, well, the residual is sort of yellow, but it's a white star, white hot star. Okay.
Excuse me.
Yeah.
In the previous slide,
Yes.
there was a peak around 100 nanometer.
I don't know the individual peaks by name, but I'll come back to that
Yeah,
diagram.
there was a peak before.
Yes. Okay. Some people do know them. I already showed you all of the field is changing all of the time. This is an odd way of looking at it. It's this model that I showed you earlier now being projected from different angles, so you can see the front of the sun tipped looking down on the North Pole and the back of the sun tipped looking down on the South Pole. The only reason I'm showing you this is all of that activity comes up in what's called the activity belt. There is never a sunspot above 30 degrees in latitude. There's never been in recorded history. Probably did happen 4 billion years ago, but not in recorded history. And yet there's field up there. That field does not emerge there as a largely unipolar field, but it comes up there being advected in the meridional flow, and it sorts itself out into a way that the polar caps are capacitors. This is important if we're getting back to the solar wind bit. The polar field is essentially the lowest order residual field of everything that bubbles up at mid-latitudes that makes it to high latitudes. And after one cycle, it gets replaced by the next polarity. And after one cycle, it gets replaced by the next polarity. And what it does in between does all sorts of fun things for the solar wind that I'll get to you right after the break. The solar cycle makes the sun change over time. It changes differentially at different wavelengths. If you look at the X-ray sun, it's an incredible spectacle in change. And if you look at the white light sun, you go, oh, that could be more exciting. But all of that adds up to what is the total solar irradiance as a function of time. And I would love to be able to show you only this picture. That now that we've looked at the total solar irradiance over about 25 years in time, we can actually show you what happens. What happens is brighter, because of all these faculae that sit on the surface when there's a solar maximum, an occasional dip, lots of dips as the big sunspots rotate over disk center and take more light away than the faculae around it add. And as the sunspot cycle fades, we level out to some flat point and comes up and goes down and goes up and goes down. And overall, it's, well, flat in one of these reconstructions. And other people say that the long-term trend is up or the long-term trend is down. And we don't know. The reason we don't know is that lots of different instruments have looked at the total solar irradiance over those 25 years. And each one of them has a different calibration. Slightly different sensitivities. The best people try to get these things on the same scale. They can't quite get them there. Every instrument ages with time. So everything has a changing response over time. So it's really difficult to get to the better than a part per thousand stability of sunlight coming down to Earth. So we still don't know whether it's flat or not. And the climate theory modelers, like the ones at the Mesa Lab you were at last night, are like, well, should we be interested in this or not? And they get different answers from us depending on whether we believe it's doing that or that or that. So that's an open field. Now, on top of that, the last bit here is everything changes also on a much shorter time scale when these large eruptions that Terry was talking about happen, the big flares and eruptions that show up mainly in the extreme ultraviolet and the X-rays. And if you're interested in total solar irradiance, you're going to conclude that this is not what you're going to be looking at because it doesn't do very much. But if you're interested in things that affect the ionosphere and the uppermost part of the Earth's atmosphere that controls, say, satellite drag, that makes a big difference. So there's a lot of people that do work on the short wavelength end, not just because flares are pretty, because they're actually important for some things. And what happens? Well, this is one of these image sets that we now take every day, and they were actually taken at 16 megapixel cameras in 8 different wavelengths, and we can't put them on the screen. Your eye can't see the 8 different wavelengths at the same time, so these are 3 wavelength composites. And there's no projector in the world that can do a 4K by 4K projection yet, at least not an affordable one. So maybe they'll get there someday. So I'm showing you this smaller, but you're basically seeing the colorful solar corona with all of its dynamics. If I had made the movie repeat, you could have seen that. Big flares, big eruptions, variability at every wavelength showing up. But you have to understand or at least measure somehow that you can get the picture of the total solar irradiance. In X-rays, the contrasts are enormous. A flare can brighten the entire sun in what's the GOES instrument that's been measuring the sun for 35 plus years. Can brighten the entire sun in the 1 to 8 angstrom passband by a factor of maybe 10,000 for the largest flares. There's some here that are several thousand times if you look at that light curve from this point up and down again. So there are enormous spectacles in X-rays. And they have different spectacles at different wavelengths. And they actually will have different timescales of evolution. The shortest wavelengths, the hottest media, as Terry was saying this morning in the question session, cool very quickly. So that's not a long-lived spectacle. But after that, you've brought all this new material up that's still hot and glowing. So the longer wavelengths in the EUV take longer to cool. And then there's the visible wavelengths that show you sort of a mix because they're sort of, at least in the chromospheric part, sensitive to conduction heating coming down, and they're mixed with particles coming down at the initial impulsive phase. So I'm not going to go into this in detail. Just remember, every wavelength has its own behavior with its own temporal scales. And in fact, just to show you just how big some of these eruptions are, I'm going to show you this kind of trick movie. The instruments we now have are so sensitive, we can throw away the signal, almost. So instead of looking at the intensity, we can look at the change in intensity. And we can do this change in intensity at every one of the channels we look at it. So this is, again, a 3-color composite. The blue changes at about 1,000,000 degrees. The green changes at about 1.5 million degrees. The red changes at about 2 million degrees. Now, the reason I'm showing you this, again, goes to what I'll come back to after the break. Some of these explosions lead to coronal mass ejections. And these coronal mass ejections propagate over a vast area of the sun. This is sped up, obviously. I'm showing you one event after another, just to drive the point home, that if these things go off, and if the field makes it into the heliosphere, the corona just doesn't just sit there and go, oh, that's a nice spectacle. It has to respond. There's an enormous explosion going off. That ripple effect goes over much of the sun. And it shows up in irradiance, obviously. I can see it here in the intensity image. If I integrated this signal, I'd still see it. Okay? So it does both shake the heliosphere and rattle the irradiance. Okay, and how much energy comes out of all of this? This is one of these diagrams where a group of people came together and said, let's look at the largest flares. Whenever you see an X, that's a large flare. I don't know if it actually means extra large, but it might mean extra large. Those are fairly rare flares. They typically have that energy of the order of 10 to the 32 ergs, which is, if I remember correctly, about 50 billion Nagasaki bombs going off at the same time. What saves us is the distance. But let's look at this in slightly different order, because I had difficulty understanding this diagram. I'm going to reorder it in terms of magnitude. As Terry said, the energy is there in the magnetic field. That's not the problem. There's more energy in the magnetic field that can ever come out in the form of a flare or a coronal mass ejection. The second largest terms and the third largest terms are, well, they're actually comparable. The amount of energy that comes out as photons is in general comparable to the amount of energy that goes out as kinetic motion, as the coronal mass ejection being thrown out, with a substantial uncertainty and change from event to event. And if you go down this list, look at where you end up at the top. The tiniest fragment is where we look at them in the X-rays. 1% or thereabouts of all the energy coming out in a flare or a coronal mass ejection comes out in the GOES light curve, which we all look at. And the reason we look at it is because the sun itself is dark there. So any spectacle is immediately a big spectacle. Fran?
Yes, the colorimetric, what dominates that power? Is that mostly the X-rays or the visible photons, or you said
Everything that gets stuck in space takes approximately half of the total bolometric light. So everything short of about 3,000 angstroms, 300 nanometers, is approximately half. The rest comes out in visible light. People used to say that white light flares were rare. The very first one that Carrington and Hodgson saw, please mention these two people together. Carrington always gets but they really saw it at the same time, and if one of them had seen it without the other, nobody would have believed them. Carrington-Hodgson flare in 1859 was the first one that was strong enough so that we could actually see the white light against the glow of the photosphere. But by now that our instruments are very sensitive, we know that pretty much every flare is in fact a white light flare. Half of the photons come out in the visible, but we don't pay attention to them terribly much because we just can't see it against the background of the bright photosphere. I'm almost done. The other thing I wanted to show you is, I'll say this. I'll say it, but you can look at it if you wanted to. Even if two events have the same amount of energy going into them, their appearance can be fundamentally different in terms of irradiance. I can create a 10 to the 31 erg flare. A low X, maybe a very high M, maybe for medium flare. I don't know how people came up with this, because below M is ABC. This doesn't make sense to me. Anyway, a high M class flare, so a substantial but not extreme flare that goes off in an active region will be very bright in X-rays. And it'll typically be pretty short-lived, tens of minutes. If I let that same amount of energy go off one of these vast structures that you see over outside of active region, a filament, a prominence, the cool material suspended in these thread-like structures over the solar surface, into a coronal mass ejection, the bulk of the energy will come out as kinetic energy, and it'll come out in the extreme ultraviolet, so hundreds of angstroms rather than single unit angstroms. And it'll take a day for it to relax. So just looking at the strength of one diagnostic is a really bad idea if you want to characterize what the impact is on the total solar radiance and measure how much energy is actually being released. Okay, last one. Now all we need to do is put it together. I'm afraid I did what Mark said you should be doing. I wrote down a few sentences of summary here. What would I like you to take away from this? We know the total solar radiance is a function of time, and the variation is dominated by the brighter faculae with the occasional dips of the sunspots. Most of those changes, almost all of the changes, in fact, let me rephrase that. There's no evidence to the contrary of what I'm going to say. The changes in TSI are dominated by the presence of the magnetic field and the structures that are formed by the magnetic field. In principle, you could think if there's that much magnetic field in the convective envelope, it could change the structure of the convective envelope. There is no evidence that it actually does that at any measurable level. People have tried. The long-term trends, neither in total nor in solar spectral irradiance, we really know which way things are going. The sun is pretty flat. It's flatter than we can get the calibrations of our instruments at present. Explosive events are wonderful to look at. They don't do terribly much to TSI, but they do a lot in solar spectral irradiance, particularly at the short wavelengths. So it's just a matter of contrast. They're huge where the sun itself is dark. And then, and that's the last thing that really leads into the second part of my talk, we tend to want to use information on centuries timescales to reconstruct the total solar irradiance that paleoclimatologists would like to have. And the only evidence we have for these changes in the sun are not direct measurements. They're basically radionuclides hiding in ice. And there's a long path, parts of which you will hear, parts of which you can read about in the books and elsewhere, between radionuclides in ice and the sun, particularly if you realize that the radionuclides are modulated by what we call the open field, the solar wind, second half, whereas everything that I've shown you today until this point is where the field is closed. And those two do not simply scale with each other, and I'll show you that next. Okay, let's take 15 minutes. And then I'll take questions, and then I'll get to the second part, okay?